classroom on calculating delta H. As always, feel free to pause this video at any time to take notes. If you remember from our last video, we found out that delta H, or heat of a reaction, also called enthalpy, is a way to describe the heat that is either released or absorbed when you do a chemical reaction. And the way you calculate it is by using this formula right here. Delta H, which is the heat of a reaction, is equal to the heat of the products minus the heat of the reactants. What I'm going to show you is 4 different ways that you can actually calculate this value. The first example I want to give you is, what if I just give you the information directly? The heat of the products, I'm going to abbreviate that as H products, is 60 kilojoules, and the heat of the reactants is 100 kilojoules. So using this formula up here, giving it in a diagram. So you're asked to calculate delta H given a potential energy diagram. So in this situation, first you have to be given a potential energy diagram like this one, and you have to be given that, once again, the reactants have 20 kilojoules of energy, this time 20 instead of 60 or 100, and the products have 50 kilojoules of energy. So notice, instead of saying the heat of the reactants is 20 and the heat of the products is 50, I'm just writing it on the line here, or maybe here I wrote 20 and here I wrote 50. So again, using the same math, it's products minus reactants. So 50 minus 20 is positive 30 kilojoules. Notice this time it's a positive number, which means this reaction is endothermic. And if you remember from the last video, this picture is exact opposite of the picture I showed you in the previous video, where I gave you an exothermic picture. This one is endothermic, and I can tell because the products have more energy than the reactants. But again, the math is still the same. You just take products minus reactants. All right, a third way to calculate delta H would be calculating it from a balanced reaction. So in this situation, I'm not going to give you a picture with a potential energy diagram. I'm not going to give you just information that the heat of reactants is this and the heat of the products is this. Instead, I'm going to give you an actual reaction. 2 carbons plus 3 hydrogens make C2H6 plus 84 kilojoules. So this means that when I do this reaction, 84 kilojoules are released. Now, how do I know that they're released? Because they're on the right side of the arrow. Again, I wrote here, note that the heat, or in this case 84 kilojoules, is on the right side of this reaction. This means the reaction is exothermic. And remember, in an exothermic reaction, the delta H is reported as a negative number. So it is negative 84 kilojoules. Now, if you're a little confused, that's because here it says positive 84, but that's because it's on the right side of the arrow. So we're saying that the 84 kilojoules is being given off. And when energy is given off, you make it a negative number. Now, opposite to this, we could show an endothermic reaction. Here it says 66.4 kilojoules plus N2 plus 2O2 makes 2NO2. Notice this time that the heat is on the left side of the arrow. You're adding 66.4 kilojoules to the left, which means that the heat, in this case 66.4 kilojoules, is on the left side of the arrow, meaning it's an endothermic reaction. Heat's entering, not exiting. And the delta H is positive 66.4 kilojoules. Now again, let's make sure we're clear on this. When the heat's on the left, that means endothermic, and the delta H is a positive number. When the heat's on the right, that means it's an exothermic reaction, and delta H is a negative number. Okay. One final way to calculate delta H is simply using a reference table, table I. And you can then use stoichiometry if you want to make it more challenging. So what exactly does table I show you? Well, let me give you a few examples here. Table I says the heats of reaction at 101.3 kPa and 298 Kelvin, and there's a list of, I don't know, maybe 30 reactions or so. And to the right of each and every one of them is the delta H in kilojoules. Some of them are negative values, some are positive values. What does it mean when the delta H is negative? Well, if you remember from just a few moments ago, I said that means it's an exothermic reaction. But in it on the reference table, at the bottom of table I, it says the delta H values are based on molar quantities represented in the equations. A minus sign indicates an exothermic reaction. So, let me show you how you solve a simple problem using table I. The example I'm going to give you is as follows. What is the delta H for the combustion of CH4 gas? Now remember, combustion means taking a compound, adding it to oxygen, and burning it to create carbon dioxide and water. So sure enough, if I look on table I can find this exact equation. CH4 plus 2O2 goes to CO2 plus 2H2O. Let me show you where that is in table I. It's the first reaction on the very top here. CH4 plus 2O2 makes CO2 and 2H2O. Not only that, but directly to the right of that reaction, it tells you that the delta H of that reaction is negative 890.4 kilojoules. So, the answer to this question is just exactly what it says in the reference table. You have to admit, this is probably the easiest question that could possibly be asked. You don't have to calculate anything. You don't have to subtract. You don't have to figure out what the sign is. It's already given. However, let's make this a little more challenging. Let's rewrite this question. Now let's say that the question reads as follows. Hold on, let me adjust this so you can see the whole question. Okay, so now let's say that the question was rewritten to say, what is the delta H of a combustion of CH4? So again, we're burning CH4 just like up here. However, I want to produce only 1 mole of H2O. So I look at this equation, and sure enough, I'm burning CH4, but I produce 2 moles of H2O. The question said, I just want to make only 1 mole of water, not 2. So, the reaction from table I shows 2 moles of H2O. How would I find the delta H for just producing 1 mole of H2O? Well, obviously, you'd have to divide by 2. I want half the number of waters produced, not 2 moles, just 1 mole. This is where stoichiometry comes in play. Here's the reaction, and when I burn CH4 and I make 2 moles of water, I know I produce negative 890.4 kilojoules. So if I only want to produce 1 mole of H2O, 2 over 1 equals negative 890.4 over x. If you cross multiply, or simply divide by 2, you get negative 445.2 kilojoules. So all you have to do is make a ratio. I could have made the problem different. I could have said, all right, this is the delta H for burning 1 mole of methane, CH4. What if I wanted to burn 10 moles of methane? Well, then you'd take that number and you'd multiply by 10. So you can make a ratio, just like you do mole to mole, you can do mole to kilojoules. You just have to know what you have and what you want. So in class we'll do some more practice with this, but pretty much that is how you calculate delta H in different ways.